Okay, let's dive in. Uh, we've looked at the area model for problem solving. We've looked at it at how to even just write down a fraction in a picture form. What we're going to do now is look at the area model as a tool for multiplication. And so we're going to start out here with just a rectangle. And what we're going to do is we are going to multiply 3/4 times 2/3. Using the area model is the way we're going to go about this multiplication. And so if I want to show 3/4 in my model over here, I'll cut this into fourths and I'll shade 3 of those. Let me know if there's anything here that you're not sure about, you're not clear about, or doesn't make sense. We've shaded 3/4. Now we want to multiply this by 2/3. So what we're going to do is we are going to shade 2/3 in the other direction. And then to get the result of our multiplication problem, essentially what this is saying is what is 3/4 of 2/3 is a good word for multiplication. What is 3/4 of 2/3? That's what we're looking at here. We look for the overlap. Where is the crosshatch? And let's see, that's going to be these 6 pieces right here. And so it's 6 pieces out of a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total pieces. So our answer here is 6 out of 12 pieces, or 6/12. One of the things I really like about this area model for multiplication is it helps your students see the standard algorithm for multiplication. Once you see this area model and you're like, all right, so 3/4 of 2/3 is right there. It's 6/12. I got it. And then you say, okay, let's see if we can find a shortcut over here. If I want to multiply 3/4 times 2/3 and I know the answer is going to be 6/12, maybe I could do this without drawing the picture. And that walks you down the road to, hey, wait a minute. 3 times 2 is 6 and 4 times 3 is 12. So when we multiply fractions, we could certainly use the area model if we want to, but instead we could just multiply numerators, multiply denominators, and that'll give us the correct answer to a multiplication problem. I think it's a cool little visual that you can use to introduce multiplication of fractions. Start with something that's sort of a picture, and then eventually work your way towards here's the algorithm that we're going to use. Since we're talking about multiplication of fractions, let's say we want to multiply some number by 2/5. What series of steps would be the same as multiplying by 2/5? I'm going to create a poll for this one and let you choose. Hang on a minute. I'm gonna change how I'm gonna phrase these. So give me just a minute. All right, there we go. Okay, so multiple choice. I'll give you a second to read those over. There's more in those than our typical poll. If we want to multiply a number by 2/5, which one of these would get the same thing done if we want to multiply by 2/5? And I'll tell you that one of them does. So if we want to multiply by 2/5, which of these would get that done? Yeah, so I guess what I'm saying is I promise the correct answer's in there. It's one of these that you're picking from. And it's all right to look those over a little bit. There's, like I said, there's more in these than our typical poll question. I think we'll go another maybe 20 seconds and then we'll do it together. All right, let's see how we did on this one. Not unanimous, but very strong agreement. Okay, and that's good. That's good. This is one that is a little bit of the roll of the dice for me because we haven't really talked explicitly about a problem exactly like this, but students tend to pick up on it pretty quickly. If we want to multiply a number by 2/5, so we have some number, whatever it is, let's say it's 10, and we want to multiply by 2/5. Now, you know that through the algorithm approach, what we would do here is rewrite 10 as a fraction, multiply numerators, multiply denominators, and divide last. And when we do that, what we're going to do is multiplying the numerators is going to give us 10 times 2 is 20, multiplying denominators, 1 times 5 is 5. Divide 20 by 5, and we get 4. Okay, so I multiplied 10 by 2/5 and I got 4. Well, that doesn't really answer the question here. What series of steps is the same as this? The most common response was multiply by 2 and divide by 5. And let's see how that works. If I start with 10 and I multiply by 2, I get 20. And then if I divide that by 5, I get 4. Sure enough, multiply 2 by 2, divide by 5. And you can see that in the algorithm. That's kind of why we're talking about this question, is the first thing we're going to do with that 10 is we're going to multiply it by 2, and then after that, we're going to divide it by 5. So if we want to multiply by 2/5, the steps that are the same as this is, sure enough, multiply by 2, and then divide by 5. Poll went really well, but if anybody has questions on that, don't hesitate to let me know. Okay, let's talk some division. 12 divided by 6. We all are comfortable with the idea that 12 divided by 6 is going to be 2. What I want you to do is think about this in a little bit of a different way than you might have with just getting the answer. And I want you to think about this question as, when it says 12 divided by 6, really that's asking us a question. How many 6s does it take to make 12? How many of these does it take to make this? Is kind of what's being asked there. 12 divided by 6 gives me 2. How many 6s does it take to make 12? Yeah, okay, no problem. That's 2. What I want to get at here, one of the things I want to lead towards, and it'll be much more relevant in our next example, but it's a perfect time for me to bring this up, and it's a key point that I want you to make sure that you're comfortable with. That division is the same as multiplying by the reciprocal. Here we have 12 divided by 6. And my claim is that division is the same as multiplying by the reciprocal. You may be thinking, why would I go through all that trouble if it's just 12 divided by 6? Well, you probably wouldn't. But trust me, we'll look at another example in a minute where I think this will be very beneficial. Anyway, 12 divided by 6. My claim is that division is the same as multiplying by the reciprocal. So instead of dividing, I'm going to say 12 multiplied by the reciprocal of 6. And I got to remember what this word reciprocal means. If I were to write 6 as a fraction, it's 6 over 1. What's the reciprocal of that? All right, Laura, Katrina, very good. So the reciprocal, I flip it over. Oops. would be 1/6. Okay, so then instead of 12 times 6, I'm going to do, or excuse me, 12 divided by 6, I'm going to do 12 times 1/6. And I'll rewrite this as a fraction. Multiply numerators, 12 times 1. Multiply denominators, 1 times 6. 12 divided by 6 is 2. Seems like an awful lot of work. By the time you got to the end here, you were just doing 12 divided by 6 anyway. You're right. You're right. This is to set up the next one, I promise. So I want you to think about division as how many 6s does it take to make 12? And then the key idea here that I really want to emphasize is that division is the same as multiplying by the reciprocal. We're going to see the real value of this in the next example. 3 divided by 1/4. Okay, now 3 divided by 1/4. I can't do this in my head. This isn't like 12 divided by 6 anymore. 3 divided by 1/4. I'm trying to figure out what that even means. Well, what that means is how many 1/4 does it take to make 3? And you may have an answer in your head after thinking about it in these terms, and that's great. But the main thing that I want to emphasize here is that division is the same as multiplying by the reciprocal. And that's what we're going to do here when we divide fractions. When we divide fractions, we're going to use this idea right here, that division is the same as multiplying by the reciprocal. And so up here at the top, this is 3 divided by 1/4. So instead of 3 divided by 1/4, what I'm going to do, instead of dividing, I am going to multiply by the reciprocal of 1/4. Let me know if you see anything that doesn't make sense or you're not sure where it came from. But instead of dividing, I'm going to multiply by the reciprocal. I'll need to write that 3 as a fraction. Okay, and then we'll multiply numerators. 3 times 4 is 12. Multiply denominators is 1. And so our answer to this question is 12. 3 divided by 1/4 gives me an answer of 12. If I start with 3 and I divide it by 1/4, the answer I get is 12. Let's see if that makes sense back here. How many 1/4 does it take to make 3? It's a beautiful setup for the area model if you want to. You could also use the length model here. How many 1/4 does it take to make 3? Well, if I cut those into fourths and I count these up, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sure enough, it takes 12 1/4 to make 3. So it makes perfect sense that our answer here to the question 3 divided by 1/4 would be 12. Let me know if you have any questions of anything up to this point. Okay. And now what I want to say to you is we started out with the number 3. We divided by 1/4 and got 12. My question to you now is true or false? Division always makes a number smaller. When we do a division problem, is our answer always smaller than what we started with? True or false? Division always makes a number smaller. Very good, Laura Katrina. Excellent. Good, Sean. All right. Yes, our counterexample is right up here at the top of the page. Division always makes a number smaller. Well, if you're thinking, well, I don't know, 20 divided by 5, okay, the 20 got smaller. And 15 divided by 5, maybe don't do 5 again. 15 divided by 3, okay, 15 got smaller. But if we do 3 divided by 1/4, our answer is 12. So we divided, but our answer was bigger than the number we started with. So division always makes a number smaller. That is false. We kind of get used to working with whole numbers and integers even, but don't forget that you could divide and wind up with an answer that's bigger than what you started with. It happens when we divide by something smaller than 1, but the main idea here is division always makes a number smaller? No, not necessarily. Kind of depends on what you're dividing. Let me know if you have any questions about that. Okay, outstanding. Mixed numbers. We did addition and subtraction with mixed numbers. Now we're going to look at multiplication with mixed numbers. One of the nice things about addition and subtraction with mixed numbers is we could work with the whole number part and we could work with the fraction part. Well, unfortunately, with multiplying, we don't get that luxury. If I want to take 2 3/7 and multiply it by 4 1/2, what I'll need to do is convert both of these into improper fractions, multiply those improper fractions, and then turn it back into a mixed number for my answer. So it's sort of a 3-step process here. Let me know if I do anything that you're unsure of, but the first thing we'll do is convert these to improper fractions. That's 7 times 2 is 14 plus 3, that's 17/7. And then for the other one, 2 times 4 is 8 plus 1, that's 9/2. Now I have improper fractions, I can multiply those. And I just do the same thing that I would normally do. Multiply numerators, multiply denominators. Well, 17 times 9, that's a pretty big number. Let's see. 17 times 9 is 153. 7 times 2 is 14. And then instead of leaving our answer as an improper fraction, since we're working with mixed numbers, we'll go ahead and turn that into a mixed number. Now, we saw this a couple days ago, so it's probably pretty comfortable for you. We'll start out by doing 153 divided by 14 to see how many ones we'll need. 153 divided by 14, that's 10 point something. Now, I don't care so much about the something, I care about the 10. So I'm going to have 10 as the whole number part of my answer. And then I have to figure out, okay, how much did this account for? That's 14 times 10, that's 140. I'm trying to get all the way to 153 here. So I'm going to need 13 more 14ths. So 10 and 13 14ths is our mixed number answer for this question. Our process here, step 1, turn them into improper fractions. Step 2, go ahead and multiply. Step 3, turn your answer into a mixed number. And it's easy to check your mixed number and make sure it's correct by just going the other direction. 14 times 10 is 140 plus 13. That's 153 14ths, so I feel pretty good about it. Let me know if you have questions on that one before I give you a chance to try one. It feels like I'm going pretty fast today. If I'm going too fast, y'all can tell me. Or if we're just doing really well, so we're going right through it, that's great. That's the best. Okay. 6 2/3 divided by 2 1/4. So one of the things you're going to have to remember here is, yes, you're going to turn these mixed numbers into improper fractions, but division is the same as multiplying by the reciprocal. Turn them into improper fractions first, then we'll do the division. So make them improper fractions. That's a division problem. Then use the idea that division is the same as multiplying by the reciprocal, and then turn this into a multiplication problem, because that's how we'll be able to finish it. Like always, if you get an answer that's not one of the ones shown, pick the one that's closest to yours and make sure you ask questions if you need to. Let's go another 20 seconds and we'll do it together. If you need more time, let me know. Like I said, I feel like I'm going faster than normal today. All right, let's see how we did. Okay, not unanimous, but real strong agreement. That's very good. Okay, we'll talk through this one just to make sure we get some numbers in here that are a little, I don't know, bigger than normal, not that pretty. What we've got here is 6 2/3 divided by 2 1/4. We're going to turn those into mixed numbers. So 6 times 3 is 18 plus 2 is 20 thirds divided by 4 times 2 is 8 and 1 is 9/4. If you see anything that doesn't make sense, you let me know. Now, division is the same as multiplying by the reciprocal. I don't really have an algorithm for dividing fractions, but I do have an algorithm for multiplying them. So I'm going to turn this into a multiplication problem. And division is the same as multiplying by the reciprocal. One thing that's important for me to point out here is division is the same as multiplying by the reciprocal, and that's said in that way on purpose. The number we're going to take the reciprocal of is the one that we're dividing by, because division is the same as multiplying by the reciprocal. So it's the second number, the number we're dividing by, that we're going to take the reciprocal of. The first one, the 20 thirds, it stays put. We take the reciprocal of the 9/4 because dividing by 9/4 is the same as multiplying by 4/9. All right, now we'll finish our way through this. 20 times 4, that's 80. 3 times 9 is 27. That's kind of a goofy one. 80 divided by 27. I don't know what that is. So let's see. How many 27s will go into 80? 2 and some. So our mixed number is going to be 2. And, well, let's see. 27 times 2 would be 54. And so 80 minus 54 leaves me with 26. And so I end up with 26 27ths still to get me the rest of the way to have 80 27ths. So 2 and 26 27ths is our answer there. Let me know if there's anything that we did that you're not sure of. If you're able to spot your mistake in there, that's great. If not, please make sure you ask about it. Okay, so that's our dividing by fractions and mixed numbers. Now we're going to do some problem solving. Now fix that one up. Yeah, Alondra, you're right. Keep, change, flip. That's exactly right. Yeah, that's a great way to phrase that. Let me go back to that last one. So yeah, it's exactly what you just said. It's keep, change, flip, and that's what gives us this right here. Yep, perfect. I like it. Wherever you got that one, that's really good. I'm going to use it from now on. So thank you. Okay, the height of a tree is 3/4 the height of a house. The tree is 18 feet tall. How tall is the house? And I wrote at the top of this one that you could do this with an equation or with the length model. I want to do it with the length model because I want to keep showing the value of those models, and that we can solve problems like this before a student knows anything about variables or algebra or any of that. So the height of a tree, so I'm going to use the length model here. The height of a tree is 3/4 the height of a house. The tree is 18 feet tall. How tall is the house? And so I'm going to use the length model here because we're kind of talking about distance. It's vertical distance. I'm just going to draw it horizontal because that's really comfortable. And the tree is 3/4 the height of the house. So it would be good to cut this into fourths. So I've cut it into fourths. And I know that the height of the tree is 3/4 the height of the house. So the tree goes that far, 3/4, all the way to here. That's where the tree is. And I'm told that the tree is 18 feet tall. Well, let's see. If the tree is 18 feet tall, and that's 3 equally sized pieces, how big is just one piece? What number would I put here if I was labeling my diagram? Very good. Joanne, Sean. Yeah, Madison, it sure would be 6. Yeah. So that would be 6. Then this would be 12. Then that would be 18. And what we're seeing here is that each little chunk of this is 6, which means going all the way to here takes me to 24. And if the tree is 3/4 the height of the house, then the house must be 24 feet tall. And you can do this with an equation, but I like using the length model just to show that we don't have to know anything about variables or algebra or any of that to solve a question like this. Let me know if you have questions on that one. We're going to do a few more problem solvings, and they're going to sort of gradually increase in degree of difficulty. Okay. Jeremy was driving the 120 miles from Mobile, Alabama to New Orleans. His car ran out of gas after he had gone 1/3 of the second half of the trip. How far is Jeremy from New Orleans? Okay, so there's a whole lot going on in that one. I'm going to read this again. Jeremy was driving 120 miles from Mobile to New Orleans. Just hearing that bit and saying, okay, he's driving, it's a distance. I'm going to try the length model for this. And we'll have 120 miles total from Mobile to New Orleans. Just a picture. We haven't done very much. We're just kind of setting ourselves up. And then his car ran out of gas after he'd gone 1/3 of the second half of the trip. All right, now that's a little bit challenging to deal with. Some of you who are really visual will knock this right out, no problem. Some of you who are more like me and can't you just give me some variables and equations, may take a little practice, but you can get there. I don't think it's out of reach at all. So he'd gone 1/3 of the second half of the trip. So I think the first thing I'm going to do is cut this in half, and that would be the 60-mile mark. And now he'd gone 1/3 of the second half. So what I want to do now is I want to take this second half of the trip right here and cut that into thirds. Because however far it is, we know that he was driving from Mobile to New Orleans, and he had gone 1/3 of the second half of the trip. So we've identified the second half of the trip over here, and we know that he made it 1/3 of that before he ran out of gas. So that's where he ran out of gas. If anything doesn't make sense, if you're not sure why I put that mark there, it's great if you want to ask. So he'd gone 1/3 of the second half of the trip. How far is he from New Orleans? So the question we're being asked here is, how far is that? Well, let's see. If 60 to 120, that would be 60 miles, and we wanted to cut that into thirds. So if we had 60 miles that we cut into third, then each one of those pieces is 20 miles. So if we label them, this would be 80, this would be 100, and let's make sure that makes sense. So let's see. We've got 60, we go 20 to 80, we go 20 to 100, we go 20 to 120. Okay, great. So what we're saying then is he's here at the 80-mile mark. He needs to get to the 120-mile mark. So how far is he from New Orleans? Just subtract. He's 40 miles from New Orleans. And that's a way to use the length model to answer a question that reads fairly complex at first, but once we get the picture put in place, and once we understand what we've been given, it falls apart for us pretty easily, I think. Let me know if you have any questions on that one. All right, very good. All right, here's a area model question. A college had to reduce its faculty by 1/6 because of low enrollment. The college now has 350 faculty members. How many faculty members did the college have before it went through this reduction? You could do this with the length model just as easily, but we've done a couple of length, so let's look at an area here. Okay, so I'm going to draw a picture of the entire college faculty. Not the most interesting picture of the faculty, but there it is. And they had to reduce the faculty by 1/6. So what I want to do is cut this into 6 equal parts. I don't know if I can draw vertical, 5 vertical lines to cut this into 6 equal parts very well, but I'll do this. I've cut it into 2 parts, and then if I cut it this way, there we go. There, 6 equal parts. So the college had to reduce its faculty by 1/6 because of low enrollment. So that means that one of these 6 had to go. And now it has 350 faculty members. My question to you is, how many faculty members are in each one of these boxes? Just one box. How many faculty members must be in one box? This leans into something that we've done before with the area model. Laura says 70. Madison 70. Yeah, this is a little bit of review here of something we've done in the past. So it's shouldn't be too much of a stretch. If you don't see the 70, it's great to ask. Very good, Katrina. Basically, we have these 350 faculty members that we need to divide evenly among these 1, 2, 3, 4, 5 remaining pieces. So there's going to be 70 in each piece. And so then if we want to know how many faculty members did we have before the reduction, well, now I know every piece has 70 in it. So I could either add up all these 70s, or I could do 70 times 6. And there must have been 420 members in the faculty before they had to reduce by 1/6. A little bit of review. We've done something like that before. This is a little bit of a new treatment on it, though, I think. Any questions on that one? Okay. Now we'll take it up to one that's pretty involved, I think. Another area model question. Oh, no, I want to do a practice first. Sorry about that. We're not taking it up there yet. In a neighborhood, 1/2 of the houses need their shutters painted. Of those, 2/3 have black shutters. If 20 houses have black shutters that need painted, how many houses are there in the neighborhood? Use the area model for this, and I'll make a poll for it and let you try it. I got excited about going on to the harder question, but it's good for us to practice one that's very similar to that faculty question. So it's the area model question, very similar to the problem we just did. And also kind of a review from when we were working with the area model before. So we'll start with a big rectangle. Half of the shutters need painted, or half of the houses need their shutters painted. So we're going to need to cut it in half. And then of those, so we're going to have to cut it into thirds the other way, just in case you're a little rusty on your area model. Maybe get an answer that's not there. Pick the one closest to yours. And problem solving with the area model can be a little bit challenging. I think it's one of those that once you get it, you've got it, but it does take a little bit of work to get there. Maybe you're comfortable with it from before and you just knock this one right out. Maybe it was shaky before and this is another chance to kind of work on it. Let's go another 30 seconds. If you need more time, let me know. And if you struggle with this, watch us as we go through it and ask whatever questions you might have. All right, let's see how we did here. Okay, not unanimous, strong agreement. I don't think there were enough answers to be everybody, but that's okay. We'll talk through this one very carefully here. A little reminder of problem solving with the area model. This will help us with the next one we're going to do too. So, okay, in a neighborhood, so I'm going to draw my neighborhood. There's my whole neighborhood of houses. Half of the houses need their shutters painted. So there's my neighborhood, and half need their shutters painted. So there's the ones that need painting. Of those, 2/3 have black shutters. So I need to cut this into thirds the other direction. And then the ones that have black shutters, well, that's 2/3 of the ones that need painted, have black shutters. And you could have shaded the top two, that's fine. You could have shaded the ones on the right, that's fine. As long as you wind up with this picture in some form with that many out of the total shaded. If 20 houses have black shutters that need painted, how many houses are in the neighborhood? Well, what we can see here then is there must be, if there's 20 houses that need their black shutters painted, there must be 10 in each box. And if there's 10 in each box, then that means there must be 60 total houses in the neighborhood. Let me know if you have questions on that. If you could do that one, that's really, really good. Okay, now we're going to go to the one that I kind of been looking forward to. In a city, 4/5 of the men enjoy their jobs and 2/3 of the women enjoy their jobs. What fraction of the population does not enjoy their job? One thing here with this one is there is an assumption that we're going to make. And we're going to make an assumption that this population is half men and half women. So we're going to go ahead and make that assumption at the start. And so when I draw this entire population, I can draw a line down the middle and say, all right, well, half is men and half is women. So that's the assumption we're making right out of the gate. Now we'll go address the information that I was given. Okay, so let's see here. This says 4/5 of the men enjoy their jobs. So I want to cut that into 5 parts. And 4/5 enjoy their jobs. So the ones that enjoy their jobs are here. So there's the ones that enjoy their jobs. Let me know if you see anything that doesn't make sense or you're uncomfortable about it or you have questions. Okay, now we'll move on to the other side here, and it says that 2/3 of the women enjoy their jobs. So I want to cut that into thirds, but I'm not going to try to do thirds this way because the question I've been given is about the entire population. So what I'm going to do is I'm going to cut in thirds the other direction. So I'm going to cut my women into thirds. And now one of the things I don't have, the way that I've drawn this is I don't have equally sized pieces inside my rectangle that is the whole population. If you look back at the problems we've done here, we have equally sized pieces all the way through the rectangle. And here, equally sized pieces all the way through the rectangle. So what we want to do in this one is we want to make sure we have equally sized pieces. So to do that, I'm going to go ahead and cut the men into thirds, just like I did the women. And I'm going to go ahead and extend these lines all the way over and cut the women into fifths, just like I did the men. Now I have equally sized pieces all the way through my picture. Okay, now I got a shade. It says here that 2/3 of the women enjoy their job. Okay, so I'm going to shade 2/3. That's going to go this direction. All right, my picture should be half men and half women. Yes, okay, it is. I want to make sure I have equally sized pieces. I do. 4/5 of the men enjoy their jobs. Yeah, that's what's shaded in there. 2/3 of the women enjoy their jobs. Yeah, that's what's shaded in there. Okay, so I've got this thing shaded, and what I've shaded is everybody who enjoys their job. The question I was asked, though, said, what percent of the population does not enjoy their job? So I want to count up everybody else. Okay, well, let's see. That's 1, 2, 3, 4, 5, 6, 7, 8. 8 boxes that don't enjoy their job out of, because it says, what fraction does not enjoy their job? 8 out of, well, got to figure out how many total boxes I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So 8 out of 30 of my boxes do not enjoy their job. So what fraction of the population does not enjoy their job? 8/30 does not enjoy their job. You could reduce that to 4/15 if you want to, but I think it's okay to leave it 8/30 here because that's an indication of how many total boxes and how many don't enjoy their job. I think it's a really cool question. When you first read it, there's an awful lot to digest in there. But it's an awesome question that we can solve strictly by drawing a picture and then using the skills we have to make that picture do what we want it to do. Let me know if you have any questions about that one. All right, outstanding. In the weekly update for this week, one of the things I said was, this is going to be a big part of this week is remainders. And now we've got to the part of the week that's going to be remainders. The idea here is, depending on what method we use to solve a problem, we are going to get a remainder that looks different. The key is understanding what that remainder represents. And so that's why it's a big part of the week, is that it's an idea that I think once we talk about it, you'll be fine. But at first glance, it can be a little bit like, huh? So let's go through this and see. Caitlin has 4 cups of flour, and a recipe calls for 1 2/3 cups per loaf of bread. So she's making bread, she has flour, 1 2/3 cups of flour per loaf of bread. And on this one, we are instructed to use the area model, so that's what we're going to do. And the question says, how many loaves can she make? Now, this is the very first type of area model problem solving we did, where we would say, okay, well, she has 4 cups of flour, and a recipe calls for 1 2/3 cups. So I need to cut these into thirds. If you have any questions about anything we're doing here, you let me know. And you can use rectangles if you'd rather. Since I use rectangles on the other stuff, I decided to use circles here, but rectangles are fine. 1 2/3 cup per loaf. Okay, so loaf number 1 is going to use 1 2/3 cups. And loaf number 2 is going to use 1 2/3 cups. And that's it. I don't have enough flour to make any more loaves. So how many loaves can she make? She can make 2. We've answered that question. Now here's the part that I want to really focus in on, is the remainder. The remainder here is what's left over. And when I'm using the area model, what's left over is how many cups of flour are left over. And I can see that, well, I don't have an entire cup. What I have is 2/3 of a cup. So my remainder here is 2/3 of a cup. Let me know if you have any questions about anything we did there. I would feel like this would be pretty comfortable because this is our very first area model solving type of thing. She can make 2 loaves and she has 2/3 of a cup left over. Perfect. Okay. Slightly different from this, not a lot different, but a little different, is if we are given the exact same question. Caitlin has 4 cups of flour and a recipe calls for 1 2/3 cups per loaf of bread. How many loaves can she make? Well, that's the exact same question, but this time we're going to do this using the standard algorithm because she has 4 cups of flour and the recipe is 1 2/3 cups. So if we just do 4 divided by 1 2/3, we'll get the answer of how many loaves she can make. It's going to be right here in our answer. Whatever we end up with for an answer, that's going to tell us the number of loaves she can make. Okay, well, let's see. I got to turn that into an improper fraction. So this will be 4 divided by 3 times 1 is 3 plus 2. So that's 5/3. But division is the same as multiplying by the reciprocal. So we're going to, shoot, I forgot already. We're going to change flip. And we're going to say this is going to be 4/1 multiplied by 3/5. And that's 12/5. Now, we don't want to answer with 12/5 here. What we need to do is turn that into a mixed number. 5 will go into 12 twice, and that'd be 10. So I have 2/5 left over. So how many loaves can she make is 2. We get the same answer we got with the area model. We better, because that's the answer of how many loaves she can make. What I want you to pay special attention to, though, is the remainder. In the other one, our remainder, what was left over, was 2/3. That represented the number of cups of flour. These were pictures of cups of flour. So this 2/3 that was left over was cups of flour. This time, what we end up with is, yes, she can make 2 loaves of bread, but our remainder is 2/5. Well, wait, one of them must be wrong then. I got a remainder of 2/3 this way, and I got a remainder of 2/5 this way. But they're both correct. They're both absolutely correct. I'm going to give Stephen a chance here. Outstanding, Stephen. This is the number of loaves that we could make. Oops, I can't spell. The number of loaves we can make with the leftover flour. So what we have is enough flour left over to make 2/5 of a loaf. Perfect, Stephen. Really good. So the remainder that we get is different depending on the method, but it's because the remainder represents different things. Here, the remainder of 2/3 that we got, that's how many cups of flour that she has left over. Here, the remainder of 2/5 that we got, that's the number of loaves of bread that she could make with the flour that she has left over. It's a subtle difference, but it's an important one. And I want you to ask whatever you have for questions before I give you a chance to try a question that's similar to this. Okay, all right, let's do it. Caitlin has 3 cups of flour, and a recipe calls for 4/5 cups per loaf of bread. The first question here is, how many cups of flour are left over? And the second, what fraction of a loaf can be made with the remaining flour? I'm going to set up a poll for this, and I want you to answer them both. And you might not need this hint, but I'm going to give it to you anyway. How many cups of flour? You're going to want to use the area model. What fraction of a loaf? You want to use the standard algorithm. All right, I'll set up a poll and let you try it. Okay, so notice nowhere in here does it say how many loaves can she make. We're just looking at the remainders for the poll. And it's how many cups of flour are left over, area model. What fraction of a loaf could be made with the remaining flour, standard algorithm. I'll stop talking and let you try it. The idea that the remainder is different depending on the method we use can spin students around a little bit. Hopefully, now that we've kind of talked about it some and you'll get a chance to experience this in some practice, you'll be more comfortable with that idea that, oh, well, the remainder is different because it represents different things. It's totally fine. If you get an answer that's not there, pick the one closest to yours and maybe make sure you ask questions about whatever it is that happens in there when we figure out these remainders. Let's go another 20 seconds and then we'll do it together. If you need more time, just let me know. All right, let's see how we did here. Okay, strong agreement on this one too. Very good. All right, let's take a look at this one then. And we're answering these questions, and it's important for me to have the knowledge going in that if a question says, how many cups of flour are left over, then I'm going to use the area model because the picture I draw is going to show it to me. So let's see, 3 cups of flour, recipe calls for 4/5. I don't think I can cut a circle into fifths, so I'm going to go ahead and use rectangles for this. And I'll have my, let me make it a little bigger than that, my 3 rectangles that represent the 3 cups of flour that I want to cut into fifths. And that's not that easy, but they don't have to be perfect. See, that one's not perfect. That's maybe a little better. There you go. So I've cut them into fifths so that I can count it up. And a loaf uses 4/5. So there's the first loaf and the second loaf and the third loaf. And I don't have enough to make another one. So she can make 3 loaves. That wasn't one of the questions, but that's true. She can make 3 loaves. And then how many cups of flour are left over? Well, it looks like 1, 2, 3/5 of a cup is left over. Let me know if you have any questions on that. Area model lets us know how many cups of flour are left over. Okay. What fraction of a loaf can be made with the remaining flour? So the area model is going to let me, I'm going to see the flour right there. So that's going to tell me how much flour is left. If I want to know what fraction of a loaf can be made, then I'm going to use the standard algorithm for this. And for that, I'm going to do 3 divided by 4/5, because if I take my 3 cups of flour and I divide by 4/5 of a cup per loaf, that'll let me know how many loaves of bread I can make, and the remainder will tell me something too. And so let's see, we're gonna Division is the same as multiplying by the reciprocal. I want to make sure you're comfortable with that sentence. Division is the same as multiplying by the reciprocal. That's what we've got here. And so we'll have 15 over 4. So let's see, 4 will go into 15 3 times. And let's see, 3 times 4 is 12. So that leaves me with 3/4 as my remainder here. I get a different remainder than I got the other way, but that's okay because it represents something different. What fraction of a loaf can be made with the remaining flour? That's what this 3/4 right here represents. So 3/4 of a loaf of bread could be made with the flour that's left over. Let me know if you have any questions about any of that in any direction. Solving that it's three loaves of bread she can make, or the area model for how many cups of flour, the standard algorithm for what fraction of a loaf is left over or can be made with what's left over, or any of the divisions the same as multiplying by the reciprocal idea, anything that you might have questions about. Okay, very good. So I have a couple of things to say about the homework problems that are assigned for this section. Number 22, it's perfectly fine if you use an algorithm there. And number 36, trial and error is not a bad